We all just kind of expect the internet to work, don't we? You stream a video, send an email. It feels, well, effortless.
It really does.
But for those of us who appreciate the engineering behind it all, there's this whole fascinating, really structured world underneath. It governs every single bit of data flying around.
Absolutely. It's like a hidden architecture.
Yeah. And today we're peeling back those layers on the fundamental blueprint, TCP/IP.
It's the system that lets billions, literally billions, of devices talk to each other. It makes the whole digital world function. Honestly, without it, modern life as we know it just wouldn't exist.
Couldn't agree more. So this deep dive is based on some really foundational networking texts, and our mission today is, well, to unpack the core ideas, a bit of the history, and that underlying structure that makes modern networking possible.
We're looking at networking models, specifically the big one, the reigning champion, TCP/IP.
Okay, so as an end user, you probably interact with the network constantly.
Oh, definitely. Whether you're at home with, say, DSL or cable internet, or maybe you're at work using the company Ethernet or Wi-Fi.
Right. And for most people, the network itself is kind of invisible. You just use the apps, the social media, make calls, search for stuff. You don't really worry about how it all connects.
And that's intentional, really. It's designed to be seamless.
But to really get what's going on, we need to shift perspective a bit. Think like a network engineer for a moment.
Yeah, step behind the curtain.
An engineer's main job at its very, very core is pretty simple. Just move data from device A to device B.
That's the fundamental task.
Yeah.
And to do that reliably, efficiently across this massive global system, well, you need a common language, a set of rules everyone agrees on.
And that's where these networking models come in, sometimes called architectures or blueprints.
Exactly. They're basically these comprehensive sets of documents. They define, collectively, everything needed for a computer network to actually function.
Okay, so what kind of documents are we talking about?
Well, there are two main types. You've got protocols, which are the logical rules, how devices should, talk to each other.
Like grammar for computers.
Sort of, yeah. And then you have the physical requirements. Things like voltage levels, electrical currents on the cables, the physical connectors themselves, the real nuts and bolts.
Got it. So you mentioned blueprints, like for building a house.
Precisely. It's a great analogy. You could maybe try building a house without a blueprint, but good luck with that.
Right, it'd be chaos.
The blueprint makes sure the foundation is right, the structure is sound, all the hidden stuff like plumbing and wiring is accounted for. And importantly, it lets different specialists, the framers, electricians, plumbers, work together without messing each other up.
Okay, so networking models do the same for tech. They let different vendors, Cisco, Juniper, whoever, build products that actually work together.
That's the key, interoperability, ensuring their products play nice together.
Which brings us to a really interesting bit of history, doesn't it? The network wars. Sounds dramatic.
And it kind of was back in the, say, 70s and 80s. You had these big computer companies like IBM creating their own ways of doing networking. These were proprietary networking models. IBM had its systems network architecture, SNA, back in '74.
Right, so every big company had its own little kingdom. What was the problem with that?
Well, imagine you're a big business.
Yeah.
And you bought some computers from IBM, maybe some from DEC, some from another vendor. Suddenly, you're trying to manage multiple, completely separate, complex networks, one for each type of computer system.
Oh, what a nightmare. Expensive, complicated?
Totally. It was a logistical mess. So naturally, there's this big push, this quest for open, vendor-neutral models, something everyone could use.
To simplify things, encourage competition, make life easier.
Exactly. And two main contenders emerged from this.
Okay, who were they?
On one side, you had OSI, the Open Systems Interconnection Model. This was a very formal effort, driven by the International Organization for Standardization, ISO, started in the late 70s.
Sounds very official. What was their goal?
A noble one, really, to standardize networking protocols for the entire planet. They designed this very structured 7-layer model, very meticulous.
Okay, OSI on one side. Who is the other?
Now, TCP/IP, it was a bit less formal, grew out of a U.S. Department of Defense project. A lot of the work was done by researchers and engineers kind of volunteering at universities. More bottom-up, you could say.
So the formal top-down ISO standard versus the more practical bottom-up DoD project. Who won?
Well, by the end of the 1990s, TCP/IP pretty much dominated. OSI kind of fell away.
Really? The less formal one won? Why do you think that was?
That's the fascinating part. It wasn't the perfectly planned, committee-designed OSI model. TCP/IP was maybe more adaptable, more tested in the real world through ARPANET and the early internet. It just worked, and people started using it. Proprietary models faded out, and TCP/IP became, well, the standard, the most prolific network model ever.
Wow. So let's unpack this champion then. What makes TCP/IP tick?
At its heart, TCP/IP is really a collection, a suite of protocols. It defines and references a whole bunch of them. And they're documented in these things called requests for comments, or RFCs.
RSCs, right. I've heard of those. But what makes it so practical?
It's just so comprehensive. It defines enough rules that you can literally take a computer out of its box, plug in the cables, turn it on, and bam, you're connected to the network.
Because the operating system, the network card, the Wi-Fi chip,
Yeah,
they all have TCP/IP built in.
exactly. They all implement parts of the TCP/IP model. It's baked in.
Now, you mentioned layers before. How does TCP/IP use layers?
Right. The layered approach is really helpful for understanding it. It breaks down the complex job of networking into smaller, more manageable pieces or functions. We usually talk about a 5-layer model.
5 layers. Okay, what are they?
Going kind of from bottom to top, you have physical, data link, network, transport, and application.
Okay, physical, data link, network, transport, application. Can you give us a quick idea of what each one does?
Sure. The bottom layer, physical, is all about the actual transmission of bits. Think cables, electricity, radio waves.
The raw signals.
Yep. Then the data link layer manages sending data over one specific type of link, like an Ethernet network or a Wi-Fi connection.
So just one hop.
Right. Then the network layer steps up. Its job is delivering data across the entire path, from the original sender all the way to the final receiver, potentially crossing many different links.
That sounds like the big routing job.
It is. That's where IP lives. And finally, the top 2 layers, transport and application, they focus more on the applications themselves, sending and receiving data for specific programs.
Got it.
Yeah.
So should we walk through how data actually travels using these layers? Maybe start at the top.
Sounds good. Let's start with the application layer. This is the layer that provides services directly to the application software running on your computer.
So not the web browser itself, but the services it uses.
Exactly. Think of protocols like HTTP, which web browsers use, or POP3 and SMTP for email. The application layer defines these standardized services the apps need to talk across the network. You're using this layer constantly, probably without thinking about it.
Okay, let's use that HTTP example. Say Bob wants to see Larry's web page. What happens at the application layer?
Okay. Bob opens his browser. The browser needs Larry's homepage, so it sends an HTTP message, specifically a GET request.
A GET request.
Right. And that message includes an HTTP header. Think of it like instructions. It tells Larry's web server what Bob wants, maybe the specific file name like home.htm.
And Larry's server gets this request.
Yep. And it sends back a response. This also starts with an HTTP header. Crucially, this header has a return code.
Ah, like 200.
Okay, that's the one for success, or, the one everyone hates, 404 not found. That's also an HTTP return code.
We've all seen that one.
Definitely. So after the header, if it was successful, Larry's server starts sending the actual content of the requested file, maybe in pieces.
Does it keep sending the header with every piece?
Good question. Often, no. To save bandwidth and be more efficient, subsequent data messages from Larry might skip the header, assuming Bob's browser already knows the context.
Okay, so the application makes its request via HTTP. Where does that request go next? Down the stack.
Down the stack we go to the transport layer. This is where we find the 2 big players. TCP, the transmission control protocol, and UDP, the user datagram protocol.
TCP and UDP, what do they do? Let's focus on TCP for a moment.
Okay, well, one of the absolute key services TCP provides is error recovery.
Error recovery. Why is that important?
Well, think about it. What happens if Bob's GET request gets lost somewhere in the network? Or maybe part of Larry's web page response disappears?
Uh-oh. Bob wouldn't get the page, or it'd be broken.
Exactly. So TCP has clever ways to handle this. It uses things called acknowledgements and sequence numbers.
How does that work?
Imagine Larry sends the web page in, say, 3 chunks. He numbers them. 1, 2, 3. Bob gets chunk 1 and chunk 3, but oops, chunk 2 never arrives. Bob's TCP software notices segment number 2 is missing. So it sends a little message back to Larry's TCP saying, essentially, hey, I missed number 2. Can you send it again?
Ah, so it asks for a retransmission.
Precisely. This back and forth ensures that applications, like Bob's browser, eventually get all the data they need reliably, even if the network itself isn't perfectly reliable.
That sounds incredibly useful, but all that checking, acknowledging, potentially resending, does that slow things down?
That is a great point.
Yeah.
Yes, it does introduce some overhead. TCP's reliability isn't free. It costs a bit in terms of latency and bandwidth because of those acknowledgments and potential retransmissions.
So it's a trade-off.
Absolutely. For things like web browsing or file transfers where you need every single bit to arrive correctly, that trade-off is totally worth it.
Yeah.
But what about live video streaming or maybe online gaming?
Yeah, their speed is probably more important than catching every single dropped bit. A little glitch might be okay if the stream keeps flowing.
Exactly. And that's where the other transport protocol, UDP, often comes in. But that's maybe a topic for another day. For now, just know TCP prioritizes reliability.
Okay, so these layers, they don't just work in isolation, right? How do they actually cooperate?
Right, it's this really neat choreography. There are two main ways the layers interact. First, there's adjacent layer interaction.
Adjacent, meaning layers next to each other.
Yep, on the same computer. This is when a higher layer, like HTTP in our example, asks the layer directly below it, TCP, to do something for it. Like, hey TCP, please handle the error recovery for this data I'm sending. The lower layer provides a service to the layer right above it.
Okay, one layer asking its neighbor for help. What's the other type?
That same layer interaction. This happens between different computers.
Ah, so Bob's computer talking to Larry's computer.
Exactly. It's when a specific layer on Bob's machine communicates with the same layer on Larry's machine, like Bob's TCP talking to Larry's TCP.
How do they talk directly if there are other layers in between?
They use those headers we mentioned. Larry's TCP puts sequence numbers in the TCP header. Bob's TCP reads that header and understands the sequence. That header information allows them to coordinate, even though the actual data passes through the lower layers. This header communication is the protocol for that layer.
Clever. Okay, so below transport, we hit the network layer.
We do, and the star of this layer is the Internet Protocol, or IP. This is the IP in TCP/IP.
And you said this is like the global postal service.
It's a really fitting analogy. Think about it. The Postal Service needs unique addresses for every house, right?
Sure.
IP defines unique IP addresses for every device, every IP host connected to the network. Those numbers you see, like 1.1.1 or 2.2.2.2 in that dotted decimal format.
Okay, addressing. What else?
Routing. Just like the post office figures out how to get your letter across town or across the country, IP defines how data gets routed through the network.
And devices called routers do this.
Exactly. Routers are like the post offices. They receive an IP packet. That's the message at this layer. Look at the destination IP address in the IP header and make a decision about where to forward it next.
And just like sending a letter, I don't need to know the exact route my data takes.
Nope. The higher layers, application and transport, they just hand the message off to the network layer and say, deliver this, please. IP and the routers handle the complex pathfinding.
So back to Bob, 2.2.2.2, and Larry, 1.1.1.1. Larry wants to send an IP packet to Bob.
Right. Larry's computer sends the packet to its nearest router, let's call it R1. R1 looks at the destination IP, 2.2.2.2. It consults its routing table, makes a decision, and forwards the packet, maybe to another router, R2.
And R2 does the same.
Yep. R2 looks at 2.2.2.2, figures out Bob is directly connected or nearby, and forwards the packet straight to Bob's computer. That's IP routing in action.
Cool. So we're almost at the bottom. What's left?
The data link and physical layers. These two work very closely together. Sometimes they're even talked about as one combined layer. Their job is to handle the delivery of data across one specific physical network segment.
The actual nuts and bolts.
Pretty much. The physical layer is the nuts and bolts.
Hmm.
The cables themselves, Ethernet cables, fiber optic cables, and the electrical signals, light pulses, or radio waves that represent the bits. It defines things like voltage levels, timing, the shape of connectors, really fundamental stuff.
Okay, the wires and waves. What about data link?
The data link layer defines the rules for using that physical medium. So protocols like Ethernet for wired LANs or Wi-Fi, which is technically IE 802.1 or wireless LANs. They manage how devices share the cable or the airwaves, how to format the data for that specific link type, and often how to detect errors that occur during physical transmission.
So when Larry's IP layer decides to send that packet towards router R1 over, say, an Ethernet cable, what happens at these layers?
Okay, great example. Larry's IP layer hands the IP packet down to the data link layer. The data link layer then performs encapsulation.
Encapsulation, wrapping it up.
Exactly. It wraps the IP packet. For Ethernet, it adds an Ethernet header at the front and an Ethernet trailer at the end. This whole new package header, IP packet trailer, is now called an Ethernet frame.
Header, packet, trailer. Get it.
Frame. Then the data link layer hands this frame down to the physical layer. And the physical layer's job is simply to transmit the actual bits of that frame, one by one, as electrical signals over the Ethernet cable.
And when router R1 receives those signals,
Its physical layer converts the signals back into bits, recreating the Ethernet frame. It then passes the frame up to its data link layer. The data link layer checks the frame, maybe for errors using the trailer, and then strips off the Ethernet header and trailer. This is de-encapsulation.
leaving the original IP packet.
Precisely, which R1's network layer can now look at to make its routing decision. This whole transmit, receive, de-encapsulate process happens at every single hop across the network.
Wow, okay, so that brings us back to this core idea of data encapsulation. It sounds like the central mechanism here.
It absolutely is.
Yeah.
It's how everything works together. As data moves down the layers on the sending computer, each layer adds its own control information, its header, and sometimes a trailer to the data it receives from the layer above.
Like wrapping a gift, then putting it in a box, then wrapping the box.
That's a decent way to think about it.
Yeah.
A nested doll of data. So let's quickly recap that 5-step process when sending data.
Okay.
1, you start with the application data, and the application layer might add its own header.
Right.
2, that gets passed down and encapsulated with the transport layer header, TCP or UDP.
Okay.
3, that whole chunk gets encapsulated again with a network layer header, the IP header.
Making an IP packet.
Yep. 4, then that gets encapsulated by the data link layer with its specific header and trailer, creating a frame, like an Ethernet frame.
Frame, right?
And finally, 5, the physical layer takes that frame and just transmits the raw bits.
It's really quite elegant when you break it down like that.
It is. And understanding this helps decode some of the jargon people use. You hear terms like segment, packet, and frame thrown around.
Yeah, what's the difference? Is it important?
It is useful for clarity. They refer to the message at different layers. Generally, a segment refers to the message at the transport layer, the TCP or UDP header, plus the data it's carrying.
Okay, segment, transport layer.
A packet usually refers to the message at the network layer, the IP header, plus whatever data it's carrying, which is usually a segment.
Packet network layer, IP.
And a frame refers to the message at the data link layer, the link header, the data, usually a packet, and the link trailer.
Frame, data link layer. Got it. Segment, packet, frame.
Knowing those helps keep conversations clear when you're troubleshooting or designing networks.
Now, before we wrap up, we touched on OSI earlier. The model that kind of lost the war to TCP/IP, does it still matter at all? Is it just history?
Ah, the ghost of networking past. It's funny, even though TCP/IP is what we actually use, OSI's terminology is still incredibly common. It's like a legacy language everyone still speaks.
Really? Why?
Well, OSI had that very clear 7-layer structure: application, presentation, session, transport, network, data link, physical.
7 layers, right? More than TCP/IP's typical 5.
Yes, but the key thing is the bottom 4 layers of OSI transport, network, data link can conceptually map pretty well in name, number, and function to the core TCP/IP layers we've been discussing.
Ah, okay, so the numbering stuck around.
Exactly. You'll very often hear network engineers refer to, say, IP as a layer 3 protocol, using the OSI numbering, even though they're working entirely within the TCP/IP network. Or they might talk about firewalls operating at layer 4 transport or layer 7 application.
So we use TCP/IP technology, but talk about it using OSI layer numbers. A bit weird, but okay.
It is a bit weird, but it provides a standard reference point. You might also hear the term PDU, Protocol Data Unit. That's OSI's generic name for a message at any layer. Yeah, and often you'll see it written like LXPDU, where X is the OSI layer number. So an IP packet, since IP is considered layer 3, could be called an L3 PDU. An Ethernet frame would be an L2 PDU. It's just vendor-neutral shorthand.
Okay, so OSI lives on, at least in how we talk about networking.
In spirit, yes.
So wow, we've gone from the internet just working to seeing this intricate layered blueprint underneath TCP/IP. We saw how it emerged historically and how each layer, from application down to physical, plays a specific role, using encapsulation to pass data along.
That's the journey. Hopefully, you now have a much richer appreciation for what's happening behind the scenes. The next time you load a web page or send that email, you'll know there's this complex but really elegant dance of protocols, headers being added, routers making decisions, acknowledgments flying back, all working together to get your data where it needs to go.
It really is amazing. Now, we spent a lot of time on TCP and its focus on reliability, error recovery, acknowledgments. But it did get me thinking. You mentioned that trade-off with speed. What if you really didn't care about guaranteed delivery? What if getting data there fast, even if some bits get lost, was the absolute top priority?
Mhm.
How would that change how you design things? Would you even need some of these layers or protocols? And what kind of applications out there would actually thrive on a model like that, prioritizing raw speed above all else? Something to think about until next time.